I don't think I have to explain that much because Antoine explained almost everything. So now it's chill time. So I was going to just make a very brief summary of what I said in my previous lecture. So what I tried to say is, or try to convey is that we can have formalism, the spin model, where you quantize the field in terms of Green's functions, and then you integrate out the photonic degrees of freedom, and you end up with a Hamiltonian that only has atomic degrees of freedom, and it looks something like this. So let me write it. So sum over all atoms, and here we have something like this. So these are the atomic coherence operators. It's the basically quantum part of the Hamiltonian, and this is the propagator of the electromagnetic field, the Green's function, that is a tensor, and it's projected on the transition matrix elements of the atom. And so how I derived this was just assuming that we have classical dipoles, okay, an ensemble of classical dipoles, and then I did a very hand-wavy quantization that was just basically putting hats on top of previously what was complex numbers. So now what I'm going to do is I'm going to quantize it more formally. The derivation is actually pretty long, so there will be some steps that I will skip. But then we will end up to something that looks like this, but it will be a bit more sophisticated. Here we have a non-Hermitian Hamiltonian, like Antoine mentioned. It's because you have dissipation in the system, but the formal treatment involves a density matrix. So we will have a Hermitian Hamiltonian and a Limblad operator that accounts for dissipation. And once I arrive to the end of this kind of more formal derivation, then I will talk about some topic that has been discussed, that is Subgradients and Superradiance, in this case in order arrays. Okay, so we will use all this framework to actually do some physics and learn about these states in arrays. So before I start, I want to say that we are going to follow some references that are basically a book by Joshi Booman, which is a really nice book on Casimir physics. It's called Dispersion Forces. So here he introduces this basically quantization protocol, and it's also based on some other papers. So for instance, let me just write them. Brunner, Wells. So there is a lot of work by Wells on this topic. It's PRA 53, 1815, 1996. And for instance, Dan, Knoll, Welsh, PRA again 66, 0638, 10, and this is 2002. So there are many references, and I mean there are also other authors that have dealt with these topics. It's just there are a set of papers that I like. Okay, so the idea is, again, we want to quantize the field in any almost arbitrary dielectric medium, okay? So if we have an arbitrary dispersive, which also means absorptive medium, and we assume that is reciprocal, which is, as I've mentioned in the previous lecture, that basically the Green's function fulfills some specific condition, but physically it means that if I have a source here and this source produces a field here, if I now exchange the source by the position of the detector, the measure in the detector should be the same. Okay, so this is Lorentz or Onsager reciprocity. And I'm going to assume also that it's isotropic, just for the sake of it. So now the dielectric function is not a tensor, it's just a constant, but it may depend on position. Okay. Okay, so then what I'm going to do is I'm going to write the following equation. So I have the same equation as before. But then I'm going to add, so this part here is basically a deterministic part. And I'm going to add basically noise, P noise, a polarization vector, that is associated with dissipation. And so, so this is the fluctuating part, okay? So there might be some fluctuating currents in the medium that are going to generate some noise. And then I'm going to use this to quantize the field. So I can write now an equation, the same as I wrote before, the wave equation for the electromagnetic field. Oh, I missed epsilon here. Is now this field is produced by this fluctuating or quantum noise. Okay. And from, again, this is the same as I had before. Before I had a current that was produced, for instance, by a dipole somewhere else. This is just some noise current, if you want. And I can then relate the electric field with this by, again, the Green's function. So I have mu0 omega square d r prime d r I r prime omega projected on here. Okay. So then what I'm going to do is, in general now, because I care about operators, field operators, they have to fulfill basically the commutation relations at any time, right? So what happens if I have absorption in my system? You could think of, well, now at t equals 0, I have defined a field operator where the commutation relations hold, but then as time passes and there is dissipation, maybe my commutation relations break down. So this is problematic, and this is what makes this quantization difficult. So what I'm going to do is I'm going to introduce some auxiliary variables, so some bosonic operators that fulfill, that are chosen to fulfill the field commutation relations. So I'm going to write now the Hamiltonian for the field that is something like this. So sum on polarizations, integral in position or volume, integral in frequency of h bar omega, and here I have my fundamental variables, f alpha r omega, f alpha r omega, okay? And then on these fundamental operators, I'm gonna impose some commutation relations, okay? And the trick is that then I'm gonna relate this noise to these f variables in a way that then I know that the electric field commutators with itself or with the magnetic field and also magnetic field commutators are, the commutation relations are fulfilled at any time. So sorry because it's a bit technical and I'm gonna skip some details, but again, if you want the actual derivation, it's like a couple of chapters in Woman's book. So I'm gonna introduce these commutation relations. So this is equal to delta r minus r prime, delta omega minus omega prime, delta alpha beta. And then I have the other one that is f alpha r omega, comma f alpha r omega. This is 0. Okay? So nothing very sophisticated. And then what I do is I write this expression, P, in terms of F. And it's going to look a bit strange. But if you believe me, it is written in a way that basically the field commutation relations hold. So then we find En is I over the square root of h bar epsilon 0 over pi, the imaginary part of epsilon of r omega. So again, we have losses in the system, so epsilon may have an imaginary part. F of r omega. Okay. So, and this prefactor makes the field commutation relations hold. And so the idea of all these fluctuating quantum electrodynamics is that you have now quantum fields that have to obey Maxwell's equations. So that's one of the important things. They have to obey certain commutation relations. And also there is some basically fluctuation dissipation theorem that has to hold as well. So these are the three rules for quantizing the electromagnetic field using Green's function. And then if we do that, given that P is related, or it generates a field given by this expression here, then we can write finally the expression for the field operator in terms of this fundamental variable. So these are operators, but they are also vectorial. Okay, so let me just write it like this. So this is the field operator at r omega is omega squared mu 0 integral on r prime of g alpha beta, so it's a tensor again, r prime omega I h bar epsilon 0 pi imaginary part of epsilon of r prime omega, and I'm almost there, f beta of r omega. Yay. Okay. So that's the field evaluated in omega, the field operator, and the total field in R is just an integral in omega of this. From 0 to infinity, and the complex conjugate, Hermitian conjugate in this case, which is basically a term that gives me annihilation, and another term that gives me creation. Okay, so this is a bit of a mess, but this is the starting point. So basically now I have a field operator that I like, that is written in terms of Green's functions, that accounts for potentially loss in my system, and is written in terms of these fundamental bosonic operators that fulfill certain commutation relations. Okay, so again, it's very technical, but it's the starting point. So once we have this field operator, we can take this field operator and write the Hamiltonian for the atom-light interaction. And this is what we're going to do now. Yes.
In the previous lecture, you had a very similar expression for the electric field, but instead like of having this term or noise term, you had like a current.
Yeah, so this was basically the typical. It's in this case, you just say that you have this this current is generated by a quantum noise, and then you relate this noise through. There is some correlations in the noise that are given by this. I just erased it, but there were like the commutation relation. It involves some delta function, so these noise operators are like delta correlated. So through that, you basically fulfill the commutation relations of the field. Okay. So then what we're going to do is, this is the field, and so we're done with the quantization, although it looks super bizarre, but then one can operate. And what I'm going to do is I'm just going to write the Hamiltonian. For now, I have, again, a collection of atoms, n atoms. So in this case, I'm really going to account for the fact that these maybe, they are quantum objects, and the atoms are in a given environment given by the electric constant R, epsilon of R of an omega. And so I assume that the atoms are, again, the interaction with the field is dipolar. So I'm going to consider just electric dipole term. Okay, so I can write the Hamiltonian using basically a multipolar approach, but I'm not going to consider things like magnetic dipole, potential quadrupole terms. I'm going to truncate my expansion into just the dipolar term. And so the Hamiltonian for the interaction between the atom and the field is the sum from j equals 1 to n, so all the dipoles, of this p operator that I'm going to write in a second, what this is, at rj dot e, also at rj. So this field operator is this annihilation and creation terms, basically, that I wrote here. Okay, but now at the position rj. And this dipole operator is just similar to what I wrote in the previous lecture. It's related with the dipole matrix element, P, and the atomic coherence operator, which, just to remind you, is just some operator that takes the atom in the ground state and basically promotes it to the excited state. And the Hermitian conjugate. Okay. Okay, so far I haven't done that much. I've quantized the field. I have written the atom field Hamiltonian. And now there is the interesting part, that is, what I want to do is to integrate out the photonic degrees of freedom. So I don't want to have any Hamiltonian or any Limblad operator or any density matrix that contains terms like these ones. I want to just get rid of them, okay? I want to integrate them out. So again, this is the same as I mentioned in the previous lecture. So once I integrate out something, I'm treating the basically photonic degrees of freedom as a bath. So again, this interaction between the atom and the field is unitary, is described by a Hamiltonian. Yet when I trace out the photonic degrees of freedom, this is now a reservoir and there is going to be loss. So to describe my system, I'm going to use a density matrix. And there is going to be a part that is called Limblad operator that will describe dissipation. Okay, so I'm going to define atomic density matrix. Which I call rho. And rho is just the trace over the field degrees of freedom of a density matrix that has information about both the atom and the field. So this is just, by definition, is just the reduced density matrix. Okay, so this density matrix only describes atoms. And it does so because I have traced over the photons. And then I can write the evolution of this density matrix. So I h bar over rho of the atom field is the commutator of the Hamiltonian with the density matrix. This is in the interaction picture. Okay, so this is just the evolution of the density matrix with this Hamiltonian that I just wrote. So I haven't done yet anything. And what I can do then is I can formally integrate this expression, right? So I'm going to do that. I get that rho AF evaluated at T is the initial density matrix of the whole system minus this term here from 0 to T of this term of T prime rho AF of T prime dt prime. So I have just formally integrated this expression. So again, I haven't done anything sophisticated, but I'm gonna start doing things now. Okay, so then what I'm going to do is I'm going to start by doing the Born approximation. So I'm going to assume that I can separate as a product the density matrix of the atom field is the density matrix of the atoms, tensor product, the density matrix of the field at 0 time, which is the field is in vacuum. Okay, so this is basically Born. So if the coupling between the field and the atoms is not strong enough, I can do this. If I go to situations such as ultra-strong coupling, where you have a coupling rate that is as large as the resonance frequency of, a qubit, then you cannot do this approximation. It will break down. This is the first thing. Yes. Yeah. So what I did is I have to do some approximation, because so far I have just done formal derivations, okay? So I have said, well, I'm going to define this as the trace over the field degrees of freedom of the density matrix that accounts for atoms and field degrees of freedom. I know that the evolution of the density matrix follows this equation, and I can formally integrate out. So once I assume that this is true, once I know this is true, then I can formally integrate out. But then I cannot still solve this problem. I need to start doing approximations. And the first approximation that I can do is I can say that the system, which are my atoms, does not interact so strongly with the reservoir. So I can basically write the density matrix of the combined system as the density matrix of the system and the density matrix of the bath, basically, which is the electromagnetic field, and I'm saying that is in vacuum. Okay? Is it okay?
Yes.
Okay. Yeah, sorry, eventually it's gonna get better close to the end, but it will get better. Okay, so then I can trace, because it's easy to trace when you have vacuum on one side. And so the time evolution of the density matrix of the atoms is given by, let me see if I'm not doing something. It's given by this. So let me write it and I will explain. Because there are many approximations that I have already done. Okay, so what I've done here is the following. I have taken this expression, and I'm going to do basically perturbation theory on this expression. And so as you can see here, I have the evolution of the density matrix of the atom is the trace over the field degrees of freedom of this matrix, but I have used the fact that I can factor this out. And then I have a linear term in the Hamiltonian, that because the field is in vacuum, it's 0. And then I stop my perturbation theory at second order. So this is the minimal perturbation order that gives me a non-zero result. Okay? So this is the equation that I have to solve. And I have done here several things that I haven't explained, but I'm going to just point to a reference. So, for instance, this is typical. This part here, there is nothing interesting. I haven't used Green's function or anything. You can just look at Scully's quantum optics. And it's the typical treatment of systems that are coupled to a reservoir. Okay? And there are a couple of approximations that I have done. I've done Born approximation, and I've done Markov approximation. So these are typical approximations that you use in quantum optics. And they involve basically that the treatment is perturbative. And the other thing that it means is that the reservoir has no memory. So I'm going to explain this a bit better. So the reservoir has broad bandwidth. Okay, so it has very short memory. So what does this mean? It means that imagine that you have an atom, and this atom is coupled to a high Q cavity, okay? So you have the line width of the atom is 10 megahertz, and the line width of the cavity is of that order. This means that you have a very well-defined mode, that is the cavity mode, and that your reservoir, which is the cavity, cannot be treated as such, because the bandwidth of this reservoir is not broad from the perspective of the atom. So if you think of, for instance, you have, this is frequency, and this is some, for instance, susceptibility of both the atom and the cavity. If I have, this is at omega atom, I have the atom responds in a very narrow bandwidth. If I have a reservoir such that the frequency response doesn't change within the line width of the atom, then this system is Markovian. If you have a reservoir where the frequency response is narrow within the line width of the atom, then this is very non-Markovian. So for instance, if you are in a high Q cavity, this will lead to the typical vacuum Rabi splitting, because you cannot integrate out the photonic degrees of freedom. If you consider atoms in free space, so the Green's function in free space doesn't have any resonance, it's very flat spectrally. So this is a very Markovian situation. And then this approximation holds. Okay, so it is not a general situation that you can integrate out the photons. It depends on which kind of electromagnetic reservoir you have. Well, even that the fact that you call it reservoir is assuming that it's a reservoir, so it may not even be a reservoir. It's just a matter that whether your field modes have a sharp frequency response or if it's something flat, okay? So if it's something flat, it's a reservoir and you don't care about it. There is no interesting dynamics basically going on in the bath. The only interesting dynamics is done by the atoms. Then you don't care about the bath. If that's not the case, you cannot do basically this derivation. Okay? Questions? Yes.
Doctor, so you away from 0 to infinity.
So this is another of the Markov approximation. It's technical. We can talk about it later if you want. Yeah. Any other question? Okay. So now we're almost done, for real this time. And we can, I erased my Hamiltonian, so maybe right here. The atom field Hamiltonian had some terms that look like sigma Eg E plus sigma Eg E minus plus sigma GE E plus sigma GE E minus, okay? So one might be very tempted to do the rotating wave approximation, which basically says that there are some terms that go, for instance, in this case, let me double check that I'm writing this right. Yeah. So this operator annihilates a photon. And so this photon is absorbed by the atom to go from the ground to the excited state, so that looks okay. Whereas these other terms that are the counter-rotating terms, the atom goes from the ground to the excited state, yet a photon is created. So these are terms that have basically oscillate with frequency very fast, and they are non-resonant. So one may be very tempted on doing the rotating wave approximation at this state in your life and say, okay, this term, I don't care about it, and this term, I don't care about it, and then I just have this Hamiltonian. It's very easy. There are papers that do this, and so this is wrong. Why this is wrong? Because you're doing perturbation theory, and the Hamiltonian appears twice. So if you just you do the rotating wave approximation at this stage, there are Casimir terms that I will discuss later that are gone. There are papers on why they have to be gone, but actually there are papers that say these papers are wrong and the second ones are the right ones. Anyway, and I discovered this through, trial and error in the beginning, because this calculation is very involved. I did this, and then I found that there are very fascinating Casimir terms between different atoms that they, of course, are not there anymore once you make the rotating wave approximation when you have to do that. So, okay. So I will discuss which terms you lose and which terms you don't lose, and so on. Okay, so then if you look at the Hamiltonian, these terms here, I'm going to have terms that look like this. So just combining all the possibilities, I have sigma G, sigma GE, J, K. So these field operators will be acting on the zeros, so I don't care about them right now. I will have also terms like sigma EG, sigma EG, J, K. I'll have terms sigma GE, sigma GE, K, J. And I'll have sigma GE, sigma EG, J, K. Okay, I'm going to have sets like this. So these terms oscillate very fast. And once you are already at this stage where you are multiplying the two Hamiltonians, then this is when you can kill them. So these terms can go. If you do the rotating wave approximation at the Hamiltonian level, you also kill this term. And this is not correct. Okay? So this is, for most of you, nobody cares. Probably 99% of you don't care, but maybe somebody is doing exactly this calculation. And so I always like to tell it because it's something kind of surprising that you do the calculation wrong and it looks like it almost worked, but then there is some unphysical results. So again, I'm not going to do all the calculations, but then when we integrate in this variable, we're going to have terms that oscillate like this, omega k plus minus omega 0, tau from 0 to infinity. So terms that come from the atoms that are oscillating and terms that come from the field that is oscillating. And then from here, I convert these terms into deltas and principal values. So what I have to do is I plug everything here. I start, doing the algebra, and what I'm going to end up is doing integrals that look like this, and I'm going to end up having terms that combine operators that look like this, okay? And from there, I can get, in the end, an expression for the density matrix evolution, rho, that can be written as if it came from the following equation. So we find a spin model that looks like this. The evolution of the density matrix is given by minus I over h bar, Hamiltonian, commutator of the Hamiltonian with rho, and a Limblad operator. Okay? And the Hamiltonian is simply h bar omega 0 sum j sigma EEJ plus h bar sum ij gij sigma EG sigma GE ij. I'm going to write what this is. And the Limblad operator is even more convoluted. So let me write it and then I'll explain. Ij gamma ij over 2. And then I have a mess here. Sigma EGI rho sigma, this is EE, EG, J minus sigma sigma rho minus rho sigma sigma. And then, so that I don't mess up, this is J, this is I, this is I, this is J, this is I, this is J. Here I have EG, here I have GE, EG, GE. Okay, so it's pretty horrible, and if I would have done all the derivation, it would have been even more horrible because it's a lot of pages. But let me summarize. I have found an expression of the field that is now quantized in terms of the Green's functions. I have done perturbation theory, and I've traced over the photonic degrees of freedom, and I have found an equation that is followed by the atomic density matrix. And if I look at how this equation looks like, that I haven't written all the terms, it looks as if it came from something like this, which is a coherent part given by a Hamiltonian and a Limblad part that is tells me about dissipation. And so let me just write that. So this is coherent and this is dissipative. And so now I just need to write what are these J's and gammas. And then we will find the Green's function again. So Jij is minus mu 0 omega 0 squared over h bar dipole times the real part of the Green's function, Ri, Rj, omega 0 dipole, and gamma ij is 2 mu 0 omega 0 squared over h bar dipole times the imaginary part of the Green's function, Ri, Rj, omega 0 p. Okay, so in the end, after all this mess, what have I gotten? I've gotten a Hamiltonian that is a term that tells me that, of course, atoms have a frequency that is omega 0. So this is a trivial part. And then there is another term that tells me about the interaction between atoms I and J. So it's this flip-flop interaction that I had already in the first part of the class when I quantized just putting hats. And this Jij, in this case, is not just the Green's function, it's the real part of the Green's function. So this is a Hermitian Hamiltonian, okay? Not like before. And then I have another term that accounts for dissipation, that is this Limblad operator. And the Limblad operator has a coefficient in front of it that is related with the imaginary part of the Green's function. So again, if we have an imaginary term in the Green's function, we will have this gamma. A case where this may not occur is, for instance, in the band gap of a photonic crystal, you don't have terms like this. There is no dissipation. Why I know that this I've performed Markov approximation, an actually born Markov approximation, is that here everything is evaluated at the relevant frequency in the problem, that is the atomic resonance frequency. Okay?
So if I may just add one comment, link that to what I've explained right now. This is exactly the same GDP we discussed about. In the case of free space, when your Green function is the Green function of single dipole in free space radiating, GIG is just the real part of the GDT Hamiltonian, and gamma ig is a real part of the GDG elaborator. And you see that we never needed the light. It's all interactions mediated by the vacuum, or here, through the structure described by the Green function. It's very important to realize that, because you do have those coupling even without the light. The light, as you see also, Anna never wrote any Hamiltonian coupling the light with the dipole. Never. The only thing that couples are the vacuum modes of the field.
Yes. It actually becomes more complicated if you go to higher order in perturbation theory. So here you can decouple the driving and these interactions. If not, then it's not additive. But yeah, up to here, yes. Okay, so then what I want to say is, well, I have made a whole thing about why I needed to do the rotating wave approximation in the right place. And this is because here I have another term, which I'm going to call H Casimir. So this Hamiltonian, just for the sake of completion, is something that looks very scary. And it's something like this. An integral of u squared omega 0 squared plus u squared, real part of the Green's function r prime u, and with a plus the same, and here I have GEI sigma GE EGJ, and the same thing. Okay, so these are terms. So one thing I haven't mentioned is when I did this, when you have these terms here that you encounter when you're integrating out the field, you have these delta terms. So these delta terms are going to give you the imaginary part of the Green's function. So these are real photons that are being emitted at the resonance frequency omega 0. And then you have these principal value terms. And so these principal value terms give you these terms, the real part of the Green's function. So these are dispersive interactions. Okay, it's not just a photon is emitted. It's a virtual photon. This part is the resonant virtual photon. These are the non-resonant terms, where you integrate from 0 to infinity in frequency, and now the real part of the Green's function has complex frequency. It's very messy. And then what happens is that if I is different from j, this term and this term cancel. So there are no bizarre Casimir interactions between I and j of this sort. If they are, if you don't do the rotating wave approximation in the right place, I think this goes, and you get these terms here. And then you may think that you have very sophisticated physics, but this is not true. Okay. Okay, so then now all this was super esoteric, and so I'm going to relate it to actually what you were discussing before, that is the vacuum Green's function, just as an example of something that makes a bit more sense. But before I do that, I also wanted to mention one thing that Antoine said is, so in general, you have this, this evolution of the density matrix that you describe with a Hamiltonian and a Limblad operator. But you can basically regroup terms of the Limblad operator and write the evolution for now a wave function that looks like this. Okay, so this is exactly the same Hamiltonian I wrote in the beginning of the class. When I did everything very naively, I just, with classical dipoles, and I put hats on top. I didn't have any density matrix, yet I told you that the system evolved according to this Hamiltonian, that now is not Hermitian. Okay, so this is the Green's function, not just the real part. It's a complex number, and it's projected on the piece. So this Hamiltonian is not Hermitian, so if I take a state, so for instance an atom in the excited state, and I evolve it according to Schrodinger's equation using this non-Hermitian Hamiltonian, the norm of my wave function is gonna decay, okay, because the evolution is not unitary. So in principle I can use this effective Hamiltonian because it's helpful because I don't have to deal with the density matrix and I don't want to think about Lindblads because they are confusing. So I can think of, okay, I'm going to evolve everything with this effective Hamiltonian, but to account for the dynamics, I have to do Monte Carlo, so stochastic wave function. So I will be applying quantum jumps. I take a state, I evolve it with my non-Hermitian Hamiltonian, and at a given time I say, have I decayed to the ground state? Yes or no? If yes, I stop my evolution. If no, I renormalize my norm, and then I keep evolving. And this is what is called a trajectory. And when I do average over all trajectories, I will recover the evolution of the density matrix. Okay, so this is Monte Carlo, but we're not going to discuss. I just wanted to mention it because you mentioned it. So, and you said that I was going to explain it, so it's like a sentence of explanation. Okay. So this Hamiltonian is actually neat because, okay, it's not Hermitian, but it conserves the number of excitations. So that's why actually you have to apply quantum jumps to drive things into the ground state. But then it's also nice because we have taken a problem that is a problem really about quantum optics, right? So it's atoms interacting with field. And we have converted it into a Hamiltonian that just has spin degrees of freedom. So it's very similar to quantum magnetism, but it's now open problem. So this is actually the XY model, if you are familiar with that, but with long-range interactions, because the Green's function, as you mentioned before, it may have long-range terms, and it's open. So it's pretty rich. Okay, so now with this, I wanted to just go to the case that is the most simple case, that is free space. So let me call this G sub 0. So imagine that I have an atom in free space. This is the most simple case I can think of. I can write my equation for the Green's function. So here epsilon is 1. And I know that this is the solution where I have a point in homogeneity. Okay? So I can find trivially, as you said in your class, the Green's function in vacuum. And let me call this R. I don't know how to call this. Let me call this Ri Rj. Ri Rj. And this R is just R I minus Rj, is so that I don't get tired of writing R's. And so this is just e to the ik R. So this is the modulus of the director vector between 2 points. 4 pi epsilon 0 k square 0 R cube. And then a lot of terms. I'm going to write it a bit different from Antoine. That's a product. Okay, so this is the Green's function in vacuum. Again, it's in Jackson's textbook. I think I didn't put any wrong signs. I did. It's this. And so we have here is just this just means 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay. So this is diagonal term, and here we have a term that depends on the orientation. Okay. So this just tells you that if you have a dipole, the polarization of the field that radiates depends on where you're looking. Okay. It's going to change in a space, depending on the direction of the propagation. Okay, so this is the Green's function in free space, and I can take that, and I can take the limit where R, that is the difference between atom I and atom J, goes to 0. Okay, so imagine I want to take my Hamiltonian and look at the case where I equals j equals 1, only one atom. Okay, so the field goes back to it. So if I do that, then I find something kind of surprising. The first thing that I find is that the real part of the Green's function, where r is 0, is infinity. So that's kind of bad. And the second thing that I find is that the imaginary part is finite. And it's a K0 over 6 pi unit matrix. Okay, so let me explain this. So this term here is going to tell me about the spontaneous emission rate of an atom, and I'm going to explain that in a second. These terms here is actually the lamp shift. So if you consider that an atom is a point, and you describe everything in terms of the Green's function, you will find that you get an infinite shift of your atomic frequency. So of course this is, you can interpret this as when you measure the fact that an atom has a frequency of 300 terahertz, this infinity is already in there. Because the atom is in vacuum and you're measuring 300 terahertz, it means that the infinity is basically cancelling another infinity. Another way of thinking about it is that, of course, an atom is not a point. Eventually, it has a physical size. So you have to renormalize this frequency shift. Okay? So this part here, we're going to assume that it's just already in omega 0, the resonance frequency. And this part here is going to give me the spontaneous emission rate that Antoine mentioned that you can calculate with Fermi's Golden's rule. Oh, I'm going to calculate it right now, just to see that everything gives the result that it should. So I have here V0 of R omega 0 P. So if I equals 1, J equals 1, so I'm looking at the same atom, okay? Let me call this gamma 0. This is the spontaneous emission rate, and this should be exactly what Antoine told us in the previous class that it was. So let's do that. I get 2 mu 0 omega 0 squared over h bar, and then I have this thing there, K0 over 6 pi, and I get basically P squared. So when I basically use the fact that I relate mu 0 with epsilon 0, in the end I get something that looks like omega 0 cubed P squared over 3 pi h bar epsilon 0 c cubed. And this is precisely the spontaneous emission rate of an atom. So it looks like, at least for an atom, this idea of using the Green's function works. And I can also write the Hamiltonian for a single atom. So it's this term there, and I only have imaginary part because I've said that the real part just renormalizes the frequency. So I get minus mu 0 omega 0 squared, and then I get a P squared, and the imaginary part that is K0, 6 pi, and an I, and then I get sigma EE of my atom. And so if I rewrite this is minus I h bar gamma 0 halves sigma EE. So this tells me that if I have an atom in free space, the Hamiltonian just describes this purely dissipative phenomena that is just, the atom is decaying at a rate gamma 0. Yes? Yeah, sorry. So G0, I'm just saying that now I'm in free space. Okay, so epsilon is 1, so up to all here are the zeros. Here I have, yeah, exactly. Okay, so with this we're done with the quantization scheme. So the Green's function, at least for an atom, works. And now what I wanted to show you is what happens when you try to apply this formalism to the physics of arrays, okay? So I'm gonna do it. Where is the left? Okay, so then I'm going to take this formalism that is precisely almost built for atoms in free space. It's very simple. And I'm going to describe the physics of subradiance and superradiance that Antoine mentioned. So I mentioned in my previous lecture that the first one that told us that when you have atoms close to each other, they're going to decay faster or slower than a single atom would was Dickey in 1954. But that this paper that is amazing, it's simple in the sense that he assumes that all the atoms are basically in the same spatial location, or they are interacting with just one field mode, like in a cavity. Okay, so this idea, one cannot, this model exactly, one cannot take it and just try to understand the quantum optics that would appear in Antoine's experiments. So what is the physics of subradiance and superradiance? Already Antoine mentioned this, so this slide is maybe a bit moot now. If you have atoms that are separated by a distance that is much longer than the wavelength associated with the resonant transition, they are not going to interact with each other. So the Green's function, if you recall, that I wrote, has basically a power law decay, right? So in the far field is 1 over r, but still it decays. So if they are very far away from each other, they should not see each other, which means that if I excite these atoms, they should emit photons at a rate given by the single atom emission rate, gamma 0, that I just wrote somewhere, that is this thing here. Okay. However, if I place the atoms close enough, basically emission of photons is a wave phenomenon, so there is going to be interference. And in the most simple case, which is a shared excitation between the two atoms, so one single excitation, I can describe the physics in terms of two collective atomic modes, which is precisely what you did for classical dipoles in your previous lecture. One mode is superradiant, and it decays faster than a single atom in free space at a rate that is larger than gamma 0. This is because of constructive interference. Another will decay slower than a single atom in free space. This mode is called subradiant, and subradiance happens because there is destructive interference in photon emission. And the question is what happens when you have many of these. So I wanted to add a slide of maybe history of how people describe atoms interacting with light. So some people, of course, have used Green's functions for a long time, but another typical model is that of Maxwell-Bloch's equations. So you have a disorder ensemble, and you send light, and this light is in some preferred optical mode. And you assume that the atoms basically interact with this mode at a rate gamma 1d, but then the emission into other field modes that are not this one, this preferred one, is done at a rate gamma prime. So then Maxwell-Bloch equations are called like that because we have an equation for the field, Maxwell part, that tells me that the evolution of the field is related with the atomic polarization density, and of course is related with the coupling of the atoms to this field mode, gamma 1d. And I have the Bloch part of the Maxwell-Bloch equations, that is the atomic equation that tells me that the evolution of the polarization density of the atoms is related, of course, with the field. But then I have here a term that tells me about decay. But this decay is basically, you don't consider that there might be interference in the emission into other modes. So this decay already doesn't take on account subradiance or superradiance. So if we want to apply again these equations to the system of Antoine, these equations will not hold. Okay, so it's like the Dickey model picture, and there is the Maxwell-Bloch equations, and there should be something in between, of course. Okay, so this part I think I already did in the blackboard, so I'm going to skip it. Okay, so now let's go to the case of before of atoms in free space. We have the Green's function in free space. And now we're going to have a collection of n atoms, and I'm going to tell you about linear optics. So what happens when you have just one excitation shared among all the atoms? And we're going to consider a 1D atomic chain, okay? So if I have one excitation shared among the atoms, this excitation can be in the first atom, so the first atom being excited, all the others in the ground state. Could be in the second atom, or it could be in the last atom, in any atom. In this case, although generally my Hilbert space is 2 to the n, the dimension of my Hilbert space is huge, it's exponentially growing with atom number, because I'm restricting to the single excitation manifold, there are only n possible states. The dimension of my Hilbert space is n. So the problem becomes very simple. I write this Hamiltonian in this basis, and this is an n by n matrix that I can diagonalize. And once I diagonalize it, is again the non-Hermitian Hamiltonian, so the eigenvalues are going to be complex. And so they are going to tell me about a frequency shift from the bare atomic resonance, and they're also going to tell me about the decay rate, which can be enhanced if a given mode is superradiant, or inhibited if the mode is subradiant. So just as a test, we can take a look to a very simple case, that is, I have an array of 30 atoms. If I have 30 atoms, my matrix is 30 by 30, so I have 30 eigenstates. And I can plot the frequency shift, normalized to the spontaneous emission rate in vacuum, and the decay rate, again normalized to the spontaneous emission rate in vacuum, as a function of the lattice constant, okay, normalized to the resonant wavelength. So again, imagine that I have atoms that are very far away from each other. They form a lattice, but the distance is 200 lambda 0. What should I see? I should see no interaction, which means I should have 30 modes which have a 0 frequency shift, and also have a decay rate that is that of a single atom in free space. So in this region, indeed, I have many modes, but all of them have the same frequency shift, that is 0, and the decay rate, it approaches gamma naught. Okay, so this part of the plot, we understand. Once we start putting the atoms closer and closer, they start interacting, and in particular, some superradiant modes appear, as you can see here. So the decay rate of these modes is larger than 1 in units of gamma 0. But the interesting part is here. So we have, once we cross a critical distance, we have very subradiant states. So this means that if you pack atoms in one line, and the distance between the atoms is smaller than half of the free space wavelength, you have states that barely decay. Okay, so this is plotted in linear scale, but this can be 10 to the minus 10, tiny. So if you put an excitation in a state like this, it should live almost forever. Okay. Yes.
What are these resonances that affect the path?
So these are geometric. It's really a geometric effect because of there is some periodicity like e to the ik0r, and it just happens to be that in exactly at k0r equals 1, 1.5, or units of 2 pi, then you have this kind of resonances. But it's related with the dimensionality, the fact that it's 1D chain. So in 2D you wouldn't have these resonances. Yeah. For this, yes, so you have the chain like this, and we're assuming 2 level atoms, and the dipole moments are like this. So you can do the same with dipoles like this. Yes. Then the shape is a bit different, but the subradiant modes still exist exactly below the same critical distance. Yeah. Yes.
Why are there like several points for the same lattice constant?
Yeah.
Several modes?
Yeah. So exactly. So because I have 30 atoms for any given distance, I have 30 different collective modes. So 30 different, in principle, eigenvalues, and they are related. The spatial mode is related with different phases in the dipoles.
And how can you know in which mode you are?
So I mean, you would excite. I mean, this is related actually with I think something that you mentioned, that these modes exist whether you shine light on the system or not, because it's really a matter of diagonalizing the Hamiltonian. They exist. It's like normal modes when you have phonons. They exist. Then how you drive the system will tell you to which ones you couple, more or less. You may couple to all, you may couple to some, just to one. It could be the superradiant, it could be the subradiant. Generally, coupling to subradiant modes is hard for a reason that I will explain in a couple of minutes. Yeah. Yes?
So, like, so in this regime, we don't really care about the symmetric wave function. Like, if I swap to Sn, I think the system shouldn't really change. Do you care about that? Like, Sn to Sn?
If you swap two atoms,
Yeah.
I mean, you cannot distinguish atoms, right? The only thing that characterizes an individual atom is the resonance frequency and the line width, and I said that they are going to be identical. So you cannot, if you swap them, it's...
Yeah, so basically, I think, I mean, the atoms basically should be indistinguishable.
Yes, in principle, yes.
So like, all the analysis are done to put in.
Sorry, can you
So
repeat?
all the analysis is done to say it's distinguishable. So any...
Oh, no, so the interaction, so so indeed, each atom is the same. So it has, in free space, if it would be alone, you know, it has a given resonance frequency and a given decay rate, and this is the same for this, for this, for this, for this. But why do I write this? Why do I write I and J? Because this atom is not going to interact the same with this one than with this one, than with this one, right? So I have to keep track of this when I write my Hamiltonian, because the field decays in the space, so it's going to interact more strongly, if you want, with this one than with this one than with this one.
So I mean, fundamentally, it shouldn't be this kind of thing.
Why not? So imagine you have...
I mean, like, we cannot really put labels on it. I mean, if they are really identical particles.
I mean, they are in a given spatial position, right? So I could say my atom is in position 0, this one is in position 1, and this one is in position 2. Then I can say now I move all of them 200 units, and it's 200, 201, 202. Then I agree, it's exactly the same. The only thing that matters is the relative distance. You can move them like this, but the relative distance is what is going to end up appearing in my Green's function and in the Hamiltonian.
Yeah. Still, I mean, after that you've got an eigenstate, which you can put labels on them. So
Yeah.
fundamentally, we require them, like, you cannot put labels on them, so not like put some symmetric vector on this.
No, yes.
There are no quantum statistics in that. They are far apart. You can paint them with colors. And
Yeah. It's just you're saying, you're labeling them as, you know, they are the first atom in the chain or the 25.
Yeah.
And then I agree that if you go to the infinite case, then, you know, you have, if you have periodic boundary conditions, then it doesn't matter whether my atom, this one is atom 1, or if it's atom 201. But then if this is atom 201, this is 202, and then it's 203. So the important thing is the relative distance between them. If you don't see it for a lattice, imagine that you have a disordered system. Then the relative positions don't matter to you as well. If you have a 2D array, they don't matter. If you have a 3D, if you have a disordered cloud, of course you can identify where they are. If you look as atom in a tweezer, you shine light, it's gonna fluoresce, right? So you say, oh, it's there, this guy. And you
why 2 electrons in an atom, we must put them in this symmetrical
we can maybe continue this later, if you don't mind. Let me show you, maybe if I show you some pictures, you believe me, and if not, we can continue during dinner. It's just I want to show some stuff. Let's skip this. Okay, so maybe this answers your question a bit. So what I'm plotting here is the spatial profile of the most subradiant mode of a chain of 20 atoms. So I write my wave function as a superposition that is given by coefficient Cj in atom J that tells me what is the probability or amplitude of probability of atom J being in the excited state. And I plot it and I found this, okay? So the important thing here is that, as Antoine mentioned before, this mode is subradiant, or a mode is subradiant because the dipole phase is anti-aligned. So if atom 1 is like this, then atom 2 is like this, atom 3 is like this, atom 4 is like this, and so on and so forth. This is how you cancel the field. if I would be looking at the superradiant mode, I would see all the dipole faces having the same sign. Okay, and in particular, you have this shape here because this is a finite chain. If you have an infinite chain, you should just see like plus minus plus minus plus minus, not this modulation. Okay. Yeah. Yes.
How sensitive are these superradiant states to, like, if you have an effect to that?
So they still exist. Actually, there might be some localized states that are even more subradiant than, the perfect chain. They are also robust to disorder, so you can add disorder and you will find that there are still subradiant states, that the scaling of these subradiant states more or less follow what you find for a perfect chain, etc., etc. So it's not really, what I mean by this is, of course, eventually disorder is going to change things, and I think Robin is going to explain much more about that. But it's not really that. What I think is important is to realize that this is not really something that can only be done in theory. If you look at an experiment, you should be able to find a way of using the subradiant states. They are not just an isolated point in parameter space, where if you have like some change in the position of the atom, everything goes to hell and you just don't find anything interesting. Okay, and then following up with this wave function, I can calculate the field in any point in a space, and it looks like this. So again, the field is basically being cancelled in any point in the bulk of the chain, and it can only be not cancelled in the edges of the chain. So then you can think of this as the atoms behaving as a light-matter interface, in particular a waveguide. So you can start thinking of subradiant states of a chain as guided modes of now a fiber that is made by atoms. And this helped me introduce the concept of subradiance in another way. So imagine that we have now an infinite chain of atoms that are separated by a distance that is below this critical distance. I can take my Hamiltonian and now diagonalize the Hamiltonian using block waves. Okay, so I can go to the infinite case, it's trivial, more or less. And I can plot the dispersion relation, okay, so the real part of the energy as a function of the longitudinal wave vector in this direction. Okay, so I can classify my states using spin waves that they all are going to have a different frequency. And so when I do that, I find some dispersion curve that is this green shape here. So this is the edge of the Brillouin zone, okay, where this is the distance between the atoms. And typically the dispersion relation is somewhat centered around the atomic resonance frequency, the very atomic resonance frequency. Okay, so that's not very illustrative. But on top of that, I can do something else. That is, I can plot the light cone. So what is the light cone? So if somebody here works on photonics, that should be also very familiar to this person. The light cone is sets of frequencies and wave vectors that are compatible with photons that propagate in free space. Okay, so in free space, a photon of a given frequency cannot have any random wave vector. Why? Because there is something called the light line that tells you which is the maximum wave vector allowed for a photon to exist. Okay, because there is the speed of light is going to relate energy and wave vector. So if I look again at my plot, I see that there are a set of modes that are inside this light cone. And so this means that they are compatible with excitations or with photons that propagate in free space. So these have to be somehow the superradiant modes, right? Those modes that can decay. Why? Because they can emit photons and these photons can escape. Then here I have a region where the dispersion relation lies beyond the light line. Means that these wave vectors are too large for any photon in free space to have. So they have to be the subradiant modes. And also from basically a wave equation, I know that this has to be true. So basically there is a relation between the total wave vector and the wave vector along the z direction and the transverse wave vector. Which means that if this one here is longer than k0, the maximum allowed, then the transverse wave vector has to be imaginary to compensate. Which means that the modes here can basically propagate along the chain, but in this direction are evanescent. So they are really like guided modes. They are confined. They cannot escape. And the only possibility for these modes to have a decay rate is if you terminate this chain. If the chain is infinite, the decay rate should be exactly 0. And just because I said that I have a very interesting Hamiltonian that is not Hermitian, I can plot the imaginary part, the line width of these modes. And I can see that indeed inside the light cone, the decay rate is larger than the single atom decay rate. As soon as I cross the light line, my decay rate is 0. So again, subradiant modes are guided modes. And the only question now is, this is true for an infinite chain. What happens if I go to reality and I have 50 atoms? How the decay rate of subradiant modes scale. So this is the decay rate normalized to the spontaneous emission rate of a single atom as a function of the atom number for the most subradiant mode of a chain of 20, 40, 60, 80 atoms. And you see that it decays as 1 over n cubed. So the longer I make this chain, the darker these states are going to be, which makes sense. Eventually, at infinity, the decay rate is 0. And I can also think about doing something more interesting. I know that if my chain is infinite, the decay rate is 0. And I also know, because I have shown you, that the emission, the decay, happens just because my chain has edges. So I could take my chain and I could close it into a ring. No? And so this doesn't have edges anymore. And so does anybody have a guess about the scaling in this case? Nobody knows? Nobody wants to say anything? Has to be faster than 1 over n cubed, right? Because it doesn't have edge.
Exponential.
It's exponential, yes. So the only possibility is it radiates because of the curvature. So then in reality, these decay rates are associated with the dimensionality of your array and with the topology. And this is very generic, so it happens for atoms in free space, but it also happens for superconducting qubits coupled to a transmission line. It's really a matter of having many atoms talking to each other in a non-trivial bar.
One quick question.
Yeah.
Always just like one single excitation in all of the items.
Yeah.
Like in all of these cases.
Yes, so this is all single excitation. Again, this is, in general, you can have many body subradiant states, of course. And I can talk about that if you want. But all this, I mean, just learning about the single excitation, I think gives some intuition. Yeah. Any other question? No? So I also made a video because things look cooler when you have a video. So what we're going to see is I'm going to excite an atom far away. And I have said that this chain behaves as a guided mode. So if I have now an atom in a waveguide, what I should see is that if I have photons that come in this direction, they interact with this atom. And if the interaction is strong, this atom behaves as a mirror. So it should get reflected. So we can take a look at if this is the case in this situation. So here we're going to see the loss population as a function of time. And here we're going to see the population of the atoms in the chain. So here I'm exciting, and as you can see, there is no loss once it starts propagating. It hits the defect. Some loss exists because this atom may radiate into free space, and basically the spin wave is reflected. And you can also flip the atom, and you will see interesting things. So here we're flipping this atom, and now the excitation is propagating along the waveguide. And in this case, these oscillations here are due to non-Markovian effects. So it's really interesting light matter interface. Okay, so I think I have time to just say a couple more things. The first one is that I have said that subradiant modes do not decay, which in principle makes them interesting because you're basically, you have a system where you have many atoms. They are, their interaction is dissipative because there is a bath. Yet because they are correlated and because they interact, they protect themselves. They do not decay. So this is interesting, but on the other hand, the fact that they do not decay means that we cannot access them. We cannot prepare them. If we send light to this array, what we're going to see is we're going to excite the superradiant modes. We're never going to access the subradiant modes in an effective way. But we can come up with protocols for doing that and making use of this physics. So one possibility is if we have, for instance, a chain of atoms, and we interface it with a nanophotonic structure. So I have said before that subradiant modes are guided modes of the chain. So I can characterize them as spin waves that have a wave vector that is larger than that of free space, but fibers also support guided modes. So this means that a photon that propagates through this fiber is going to excite a mode in these atoms, or a set of modes that are going to be superradiant into the fiber, subradiant into free space. So this is precisely what you want if you want to do a perfect light matter interface. A strong coupling to the mode that you care about, zero coupling to any other modes that do not interest you. And you basically can play these games through interference. And the idea is very simple. It's just the fact that, again, if I plot the same dispersion relation as before, and on top of that I plot the dispersion relation of a mode in a fiber, because it supports guided modes, it's going to lie beyond the light cone, and it's going to couple to these subradiant modes. So this is generically true. And I wanted to show you an application where this phenomena can play an important role. So there is such a thing called quantum memory, where basically it's called quantum memory, but in reality it's also one of these things that could be called classical memory. But anyway. Okay, so the idea is that you have a photon or a coherent state, and you want to map it into ensemble, okay, and store it there, and after some time you want to retrieve it. So there is the process of photon storage and photon retrieval. And this protocol is very well studied, and this paper is nice because they analyze how well this protocol works, and they say that basically any protocol that is about photon storage and retrieval only depends on the optical depth of the medium. That is basically something like this. So this is the atom number, the strength of the coupling between the atom and the fiber guided mode, and this is the spontaneous emission rate into free space. So this is true if you consider that the spontaneous emission rate into free space, gamma 0, I've been calling before, is independent. But if there is correlation through free space, this has to break down. And we know that if the atoms are placed at a distance that is smaller than lambda over 2, then this is not true. So we could do much better. And just as an example of application of light matter interface, is just I wanted to explain a bit about how quantum memory works. Quantum memory requires atoms that have two ground states or one metastable state. We start with atoms in the ground state. We send a photon. This photon excites the atoms in a superposition. And with an external control field, a laser that I send, I'm going to map the population into these S states. And I switch off the laser, and I have stored my photon in a superposition of G and S of all the atoms. And then eventually, this could live forever. In reality, this is not the case, but for the sake of theory, let's assume that this is the case. And so I come back, and I can do the time reversal process. I switch on my control field, and eventually my photon is going to decay, and this is how I retrieve it. Okay, so this is photon retrieval. And the question is, where is the error in this protocol? The error is because when you are in the excited state, the photon can be emitted into the waveguide, and I can get it, so that's good. But it can also be emitted into free space, and then I lose it. So that's the error. This is what is called infidelity. I'm not retrieving all the photon, or I'm retrieving 90% of the photons, but not 100% of the photons. So we can take a look at how to deal with this problem. So this is useful because we have done a Green's function approach. So once you have a fiber, I've told you that you can find the Green's function of a fiber, and it has guided modes, and the Green's function looks like this. So here is the coupling between the atom and the guided mode, gamma 1D, and here this propagation, this phase is just how the light propagates through the fiber, okay? There is nothing special, it's just a 1D reservoir. So it looks like this. And there is also the free space Green's function that now is a bit modified by the presence of the fiber, okay? So you could just do free space here, but we were sophisticated and considered the modification of free space by the presence of the fiber. But we can also calculate that exactly. And so once we do that, we can calculate whether you can take advantage of subradiance, and this is the answer. So this is the error that you make in your memory versus atom number. This is the previous scaling, and you can do exponentially better, okay? So this means that if you use, for instance, Antoine's arrays as light matter interfaces, you can improve protocols way beyond known error bounds. And then there is a lot of exciting physics that one can do. And so with this, I think I'm very close to the end. I just wanted to have a final slide to, I don't know, start some controversy. That is, I've been into small fights about this. And it's whether subradiance is classical or quantum. Any thoughts about the matter? I mean, already you said, we have subradiant modes for classical dipoles, so you have killed my question. But I'm sure somebody may oppose. I mean, any debate about this? No, everybody thinks nobody thinks subradiance is a purely quantum phenomenon because this happens all the time. No? Okay, good. Yeah, so it's not, in my opinion. And so subradiance is just a matter of interference. Whether the fact you happens to have Bell states that look like they are subradiant, they might be subradiant, but the only quantumness is because you're saying that you have one excitation. So if all the things that I've told you before involve basically one excitation, if you calculate the field emitted, if you calculate the phases in the dipoles, if you change atom by piece of dielectric, you will find the same phenomena. It's really interference. The only difference is when you have maybe more than one excitation, so many-body physics. Here, the two-level nature of atoms is going to really come into play. If you have several ground states, you may have subradiant states that are by no means, at least that I know of, cannot be connected with anything that is classical. And I don't know if I can think of other situations, maybe other situations, but so that's it. Okay, so with this, thank you for your attention.
Could you go just please back to the slide with the string of atoms?
There were many strings, so you have to specify.
With the radiation. with the blue back and
Yeah, okay, get in there.
yeah, this one, okay. So in principle this is on first and the last one. This should then be just the probability to find like a photon as a curve, because in some sense could not be like the radiation itself, because it's just like one excitation inside, and therefore you can only just measure one photon.
I mean, you can say also it's a coherent state that doesn't saturate your atoms.
Okay. But
So, okay, imagine that so this is magical, right? Because nobody will ever see this. Because what I've done here is I've taken Mathematica, I have looked at the subradiant mode, I have chosen this as the state that is going to radiate. So it's not really excited in any physical way. But then assuming that magic happens and I can have this state, then your question is like, if this is a single photon, you can just measure it once? Yes, so you prepare it, you measure the photon, it happens to be here.
Yeah.
Then you prepare it again, it happens to be here. And so on. And eventually, by repeating many times, you would reconstruct this.
okay. Good. And then one other question. So if you like prepare this one thing like excitation, superradiance state somehow.
The superradiant state, yeah.
And no, sorry, subradiant state, and then take like one of the atoms from the end and bring it like to 20 lambda apart or something like this. Would you then, in principle, more often detect the photon to be from this one than from the other one?
I don't know what you asked, but I'm going to answer. So your question is, imagine that I have prepared this state. So first, if you move so there are a lot of time scales involved in this problem, right? So how fast you move it? Because if you move, you move it really fast, then, if you have 20 atoms here and you move it really fast, this one here, this is the state that we assume that has remained the same, yet the position has changed. It's no longer an eigenstate, right, of the Hamiltonian. Anyway, then I would say whether you detect the photon mostly from here or mostly from there, I don't know, my feeling is like if you remove probably another question, maybe if you remove here this atom, does the pattern that is radiated change a lot? I think the answer is not. So just moving one atom far away, I know. But again, this is very non-physical question, right? Because how do you even excite this? You could think of, well, if I focus a laser into this atom, then the excitation is going to start propagating. Yeah. And then it's going to leak here, for instance, and some of it is going to go back. And then your question could be, what if now, in this magical moment that is hitting this atom, I move it? Then maybe it radiates. But my point is there is a lack of physical context, no? Like there is this, if you tell me about an experiment, then maybe I can answer, but this is really...
Other questions?
Yeah, I have a question regarding the paper of the Newton and
Yeah.
Can you show the picture of the atoms on a fiber of with the gamma?
Yeah. Oh yeah, sure. Too many animations, sorry. This thing?
Yeah. So you say that infidelity is due to the fact that you can that the excitation can be
Emitted somewhere else.
to free space. So is it like can I have a better infidelity? I mean smaller infidelity just by geometry, just by like adding, I don't know, another fiber
On top?
and is it like a geometry thing, or is it like or does it not change anything?
Yeah, I mean geometry of course matters. So so the things that matter is the coupling of the atom to the modes that where you're gonna detect the photons. And then geometry matters because geometry is gonna modify the Green's function, right? So like if you put another fiber, this is gonna change the Green's function, is gonna change your Hamiltonian, is gonna change how the atoms emit light. So yes, if you put another fiber, which I don't know honestly why you would do that, but if you do that, then yes. So for instance, another possibility is, imagine that you want to have something called a slot waveguide. So slot waveguide is you put a fiber, and then in this fiber supports guided modes that decay evanescently, right? So exponentially from the surface. So if you put now another fiber, so typically this is not done with fiber, it's done with like flat waveguides. This is called a slot waveguide. And so if the gap between them is smaller than the decay length of these evanescent modes, then you confine the field in the gap very strongly. And then you would have very strong interactions between the atoms and these new guided modes that are the guided modes of the slot. So yes, geometry matters.